All right, so today we are talking about impulse. Now, in class, at the very start of class, we went outside and did a demo where we looked at two different scenarios. In one, I took an egg and chucked it at the wall as hard as I could. When the egg hit the wall, obviously, it exploded into a bunch of little pieces and stuck to the wall, right? But then in the second scenario, I said, well, what if we want to throw our egg at something, but we want it to survive? So in that case, I threw an egg, this time rather than on a wall, at a bed sheet. So the egg hit the bed sheet and then just kind of rolled to a stop and survived that time. So today, when we're talking about impulse, all of this is going to kind of circle around to these two examples and why the egg exploded when it hit the wall and why it survived when it hit the bed sheet. All right? So let's talk about our wall scenario over on the left here. Let's say that the egg had a mass of about 0.2 kilograms, sorry, 0.02 kilograms, and I threw it at a velocity of 5 meters per second. So, question is, do we start with momentum? Does the egg have momentum when I throw it? Yes, it does. It has mass, it has velocity, and those are the two things we need in order to have momentum. And then the egg hits the wall and explodes. Does the egg have momentum after the collision with the wall? The answer there is no, right? Because it has stopped. It has fully stopped when it's hit the wall, so it now has zero velocity, which means it has zero momentum. Okay? On the other hand, we have our other egg here. Let's say it's got the same setup, right? 0.02 kilograms and a velocity of 5 meters per second. So it has momentum. We throw it at the bed sheet, and then it has no momentum because it comes to a full stop. But this time it survived. So we got to figure out what the difference is between these two. But before we do, we got to define what impulse is in general. Now, we're looking at these scenarios and we're seeing that momentum, the amount of momentum in our system, which is the egg, is changing, which kind of goes against what we've been saying for the past couple of days about conservation of momentum. But conservation of momentum came with one rule, one caveat, that momentum was conserved only when there were no outside forces. So that means that now we have these outside forces that are changing the amount of momentum in the system. This is where impulse comes into play. Impulse is simply just a change in momentum. That's it. It is a change in momentum. And we have an equation to solve for the amount of impulse that a object is experiencing. So when we're solving for impulse, there are actually two ways to solve for it. It's represented by the capital letter J in equations. And the first way to solve for it comes from our definition up here. Well, if impulse is just a change in momentum, then if we solve for how much the momentum has changed, that's your impulse. Perfect. And then there's the second way to solve for it. The second way to solve for it is simple, and we can derive it by looking at the two scenarios that we were talking about, the egg and the bed sheet. To start, we know that an impulse can only occur when there is a force applied to the system, right? That's the rule. Momentum can only change if there's a force applied to a system. So let's put that force in our equation. It has something to do with force. Then if we look back at our two examples over here with the wall and the bed sheet, the main difference between these two is the amount of time that the collision takes. Over here at the wall, when the collision occurs, it happens in a split second, like 0.0003 seconds for the collision to occur. But when the egg hits the bed sheet, it takes longer. The bed sheet, it kind of bends and folds with the egg, and it actually elongates the collision. So time is our second factor here. This is our equation for impulse right here. You can either solve it by finding the change in momentum, or you can multiply force times time. And this is why the egg was able to survive, because in both cases, both objects experienced the same change in momentum, right? Same mass, same velocity, both of them come to a full stop. But in the case of the bedsheet, the time was a large number. So if the change of momentum has to stay the same, but time is a bigger number, that means force will be a smaller number. And in comparison, when the egg hit the wall, the time is a really small number. That means that the force is going to be really large, and that's going to crack our egg. Okay? All right, let's look at this for a quick second. Now, when you actually look at a force by time graph for a collision, it's going to look more like this here. It's not one singular force the whole time. It's changing, right? And to solve for the impulse, technically what we would need to do is we would need to solve for the whole area under this curve. But we don't really do that in this class, right? We don't really do calculus. So how do we reconcile with that? Because we still have an equation to solve for impulse, right? Looks like this. But what does it mean in terms of this graph over here on the left? Well, what we're actually solving for when we solve for force right here is we're solving for the average force over the course of the entire collision. So what ends up happening is we multiply the amount of time over which the collision occurred by the average force, which is somewhere around like here. We'll call that the average force. And we create this box that kind of looks like this. Well, if you notice, if I were to take this top shape over here, split it in half, and put it in this right here, those line up pretty well. Not perfectly, my drawing isn't great, but they line up pretty well. What I'm saying here is that when we take the average force and multiply it by the time over which the collision occurs, we are taking the area under the curve. It's just not being done using calculus. All right, let's do a practice problem here. Here I've got a hand karate chopping a block of wood. We know that the hand is moving at a velocity of -10 meters per second. The hand has a mass of 1.5 kilograms. It moves down, hits the block of wood, and comes to a complete stop. I have to solve for the impulse experienced by the hand, as well as the force that the hand is applying to the wood. All right? And we know that the collision occurs in 0.002 seconds. So, here's how we solve this one. We're going to use our impulse equation, obviously. We're going to look at the change in momentum. That's what we care about right now. So, mass times final momentum minus mass times initial momentum. So we're going to plug in our numbers here. We got 1.5 times our final momentum. Well, that's 0 because it comes to a stop. And then 1.5 times our initial momentum is -10. So our impulse, our change in momentum, will come out to a positive 15 kilogram meters per second. That's something we didn't talk about before. The units for impulse are the same as momentum because it's just a change in momentum. So I'm going to hold on to this. I'm going to erase what I wrote here. There we go. And I'm going to hold on to this and move it up here. That is our impulse. So we have solved for impulse over here. Now we are going to take that and set impulse equal to force times time. We know that impulse is 15. We're solving for force, and we know that time is going to be 0.002 seconds. So we plug that into our calculator, solve for F, comes out to about 7,500 newtons. There you go. That is the impulse and force experienced by the hand. All right, next thing I want to talk about real quick is just going to be center of mass. We've kind of been using this concept in class already, just without really talking about it. I just wanted to clarify what it really means to us and why we care about it in this class. Because here's the thing. When we're solving for our equations in physics, most of the time the way the numbers work out is essentially we're thinking of the objects as a single point, right? A single point that is moving up, down, left, right, whatever. But in reality, when you have an object like my box that I've drawn here on the left, it's not just one point, right? The object is here, and it is here, and it is over here as well. So how do we reconcile with that fact? How do we still do the math while we have these 3D objects that take up space in our world? Well, that's where center of mass comes into play. Center of mass I define as the average position of an object. It's the average position of an object. And it actually has an equation that we can use to solve for it. To find the position of the center of mass, what you have to do is you have to multiply the mass of one object in the system plus the mass of another object in the system, plus the mass of a third and a fourth and a whatever, however many times you need to. And then you divide it all by the masses all added up. So this is how I would find the average position of an object. Now the unfortunate part is when it comes to like 3D objects, in order to do that most accurately, I would need to run this equation considering every single particle in the object, which would take a lot of time. Here's the nice thing about this class. You don't actually ever have to use this equation. You don't have to solve for the position of the center of mass. But you have to know why it's important, how we use it. Also, you're going to be expected to essentially guess the average position in a situation like this. Let's say we got a big ball on the left here, a small ball on the right. One has way more mass than the other. You have to tell me where is the center of mass. Okay, well, it's going to be closer to the bigger one because it has more mass. That's where the center of mass is. Other important things that we're going to need to know for this class is that the motion of the center of mass is rather uniform, even when crazy things are going on in the system. So I'm going to write down motion of center of mass is uniform unless acted upon by an outside force. So all this to say is a lot of times you might have a kind of wacky system where the objects in it are moving in weird ways. But if you look at just the center of mass of that system, you're still able to analyze the motion from the standpoint of the center of mass because it's going to act in a much more uniform and understandable way than even if the whole system is acting kind of weird. All right? That's pretty much all I need you to know for center of mass. It's kind of just a helpful thing to keep in your brain because I'm willing to bet that some question on the AP exam will bring up center of mass, and I want you to be prepared for it. All right? So hopefully this was helpful, and I'll see you later.